Well, I've kind of described for you the general nature of this exchange reaction. But what I'd like to do next is to have you look at the graphic, and we'll go through and we'll discuss a graphic that visually shows you this process of cation exchange that I've been discussing up to this point in time. On the graphic labeled cation exchange, we'll start out over here on the left-hand side. This square with these little dashes in it is drawn to represent a soil mineral particle. Let's say this is a particle of a clay mineral in the soil. These negative charges or dashes are found on the surface of that clay particle, attracted to and held at these negative exchange sites, or these negative charges sites, will be cations. I put calcium on there, Ca, with 2 positive charges. I put some hydrogen on there. H is a chemical symbol for hydrogen with 1 positive charge. Now, yes, this is on an equivalent charge basis, meaning that it takes 1 negative site on the surface of the particle to hold a hydrogen cation, since it has a charge of +1. It would take 2 of these negative sites to hold a calcium, since each calcium cation has a charge of +2. So let's say that we've got an equilibrium established in the soil to where we have this type of proportion of cations being held on the surface of the exchange sites. If we were to come into this soil and add a fertilizer material, in this case potash or potassium chloride, this potassium chloride is going to break apart, dissociate, or go into solution and form potassium cations and chloride anions. What I have essentially done is to not change the concentration of calcium or hydrogen that are in the soil solution, but their concentration has now been changed because I have increased the concentration of potassium cations in solution. This would be a very great concentration increase in the immediate area where that fertilizer had been applied to the soil. What will happen? Well, what will happen is the process of cation exchange will take place to try to reach a new equilibrium in this soil. Potassium chloride will go into solution. I will now have, because of a much higher concentration of potassium in the soil solution, potassium going onto these exchange sites in the soil particles. So here I'm representing after cation exchange has taken place, showing potassiums now held on the surface of these soil particles, but I'm also showing some calcium and some hydrogen still being there. Only if I increase the concentration of potassium to an extremely high level would I get total displacement of all of the other cations from that soil particle. If we're shanking a fertilizer into the soil in that immediate shank zone or vicinity for a short period of time, I could actually see 100% displacement of all of these cations by potassium. But let's say I broadcast this and worked it into the soil, I would get this type of a representation on the soil particles. Well, if I put these potassium onto the soil particle, what has happened to the concentration of cations that are in the soil solution? Well, down here at the bottom of this, I'm saying in solution. In solution, I will have a very high content of potassium. It has to be there if it's being found in high concentration on exchange sites. I will have some calcium that got kicked off of the exchange site. I would also have some hydrogen, which was removed from the exchange site over here. It has to now go into soil solution. And even though it doesn't enter into cation exchange, I'm now going to have a very high concentration of chloride anions, which are coming from the initial compound, potassium chloride. They will also be building up at a fairly high level in the soil solution in the immediate vicinity of where I applied the fertilizer. So this is kind of a quick visual picture of what will happen to every one of these soil particles in the soil, and I'm only representing one soil particle here, but this is what will happen to every soil particle that has cation exchange sites on it in the soil as I apply a fertilizer material to the soil. In this case, we're adding potash or potassium chloride. So one more quick review. Cations that are previously being held will be displaced because their concentration will be now much less than it was initially in comparison to the potassium concentration. Because potassium concentration has gone so much higher, I will see a fair number of the exchange sites, or a pretty good percentage of those, now occupied by potassium. I'll still see some of the other cations, but a lower proportional amount. And in solution, I will have a high concentration of potassium. I will have additional calciums and hydrogens that have been removed from where they were previously held on exchange sites. And then, of course, the anion will stay in as a free cation in the soil, or not a cation, but a free ion in the soil solution, as being derived from this initial potassium chloride up here, fertilizer material. To a certain extent, I've oversimplified this process that I've just gone through on cation exchange. And by oversimplifying, what I mean is that we are not only looking at one particle, soil particle, where this is occurring on, but we're looking at literally hundreds of thousands of soil particles within a small volume of soil where this exchange process is taking place. For the purpose of the example, I'm showing what would happen if one cation's concentration were changed in relationship to the others. But in reality, most of the time we have a very constant, ongoing, fluctuating equilibrium reaction occurring, because we're not just affecting the concentration of one cation at any point in time. More often than not, we are changing the concentration of all of those cations in comparison to what they previously were anytime we affect one or more of them, through the addition of a fertilizer, through the uptake of nutrients by plants, through fixation processes. Processes can take them out of solution and not put them on exchange sites, but put them into insoluble compounds. All of these types of chemical reactions are occurring in the soil pretty much on a non-stop basis. So we need to take a little bit deeper look at this and say, okay, what is going to determine which cations are actually going to be on that particular exchange site at a given point in time? And that leads us into the concept of what are the principal exchangeable cations that do occur in the soil. And by principal, what I'm saying is that there are many different types of cations, or elements that do occur as cations or positively charged ions, but not all of these, for various reasons, enter into this cation exchange process. So what I'd like to discuss with you next is going to be what are the principal exchangeable cations that occur in the soil. We can further subcategorize these cations as those that are basic versus those that are acidic. And finally, look at what is referred to as the adsorption affinity series. And what this is it's saying that which of these cations have the greatest force of attraction to being held on the surface of these exchange sites. So that if two cations are there in equal concentration and there's only one exchange site open, which one, if we want to think of it this way, which one would outcompete the other for that being located on that exchange site? And that is referred to as an adsorption affinity series.